Hello, welcome to Quantum Online Academy. This is your Dr. Nagaraju Pendam. In this video, we are going to discuss about a 2025 Nobel laureates. What is their theory? Why this theory is coming from initial stage to now onwards up to the getting the Nobel Prize? Who did this work? What is that work? Each and everything I have to explain in this video clearly. This video is very useful to you whoever aspirant to for the scientific nature, whoever want to become as a scientist, so whoever want to give back to the society, whoever concentrate on the research, how the research is going on from one thing to another thing, how it is updated, those things we have to discuss in this video. Clear? So before entering into this video, so please subscribe and touch the bell button of our video. So this time 2025 year, 3 people got the Nobel Prize in physics field. So what are those 3 people? Once you have to see the Nobel Prize in physics 2025. So is the person John Clark. John Clark is the guide. Under his guideship, so the is a Michael H. Devarath and John M. Martinis. So this Michael H. Devarath is a postgraduate student, postdoctoral student. So his student is postdoctoral student. After PhD, he joined. So he did the PhD in France and he joined under his postdoctoral fellowship. He joined under his John Clark. He is the PhD student, senior PhD student John M. Martinis. So these 3 people did the research in the University of California, Berkeley. Clear? So these are the 3 main popular people are there. Is from London, is from France, is from USA. So these 3 people born in different countries, but they worked in USA, that University of California. Clear? So now we have to discuss one by one. What is the thing? It is a big long video, so you try to inculcate that one. In 2025 Nobel Prize in Physics, John Clark, already I told you, is the guide. John Clark is a guide. Clear? So is guru for that institute. So Nobel Prize in Physics 2025, he born in 1942, Cambridge, United Kingdom. Where he born? In UK he born. So affiliated at the time of the award, University of California, Berkeley. So USA. So what is this discovery? For the discovery of macroscopic quantum mechanical tunneling, energy quantization in an electric circuit. For the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. So for this discovery, they got the Nobel Prize for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. The second person is Michael H. Devarath. He also got the Nobel Prize in the same field. He born 1953, Paris. From France he born. Affiliation at the time of award, Yale University, New Haven City, USA, University of California, Santa Barbara, CA, USA. For his discovery, the same discovery is there because the same group did the research for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. He born in the France. Clear? As a postdoctoral student, he did the research. John M. Martinis, he got the Nobel Prize in 2025. He born in 1958, USA. Affiliation at the time of award, University of California, Santa Barbara, CA, USA. What is his motivation? For the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. He is a PhD student. So he is from USA. Already I told you 3 scientists are there. One is guide John Clark. he joined in the University of California. He did the research in his team. So Michael H. Devarath and John M. Martinez joined as students. He assigned their work. So these people discovered today's Nobel Prize theory, that is for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Why it is very, very important? In 1925, Warner Heisenberg, in 1925, Warner Heisenberg, the first invented the quantum mechanics, is the German physicist. He invented a matrix mechanics. Which mechanics? Quantum mechanics. He invented that mechanics is the matrix mechanics. Quantum mechanics he discussed in the formulation. That formulation is matrix mechanics in 1925. So 1925, 100 years you have to add it, 2025 you will get it. So this is a 100-year story, because once you want to do the research for 100 years, it should be prolonged, not only 100 years. So years together that should be burning. That research area you have to choose. That is very, very important option. 100 years later, United Nations declared 2025 year, that year is the International Year of Quantum Science and Technology. What is this year? This year is a International Year of Quantum Science and Technology to celebrate the centenary of the breakthrough. So that's why, so this year Nobel Prize chairman, that chair of the Nobel Committee for Physics, Ole Ericsson, said that it is a wonderful to able to celebrate the way that the century old quantum mechanics continually offer new surprises. It is also anomalous useful. Quantum mechanics is the foundation of all digital technology. So this 100-year-old quantum mechanics is continually uses for a new surprises and anomalously useful in quantum mechanics and digital technology. What is this year? This year is the International Year of Quantum Science and Technology. So what is the discovery of the Warner Heisenberg? In 1925, he discovered the matrix mechanics formulation for the explanation of the quantum mechanics. So who decided this quantum mechanics Nobel Prize 2025 physics? The Royal Swedish Academy of Sciences has its aim to promote the science and strengthens their influence in society. For that purpose, the Royal Swedish Academy 1901, they started this academy. Royal Swedish Academy of Sciences aims to promote the sciences and strengthens their influence in society. The Royal Swedish Academy of Sciences has decided to award the Nobel Prize Physics for these three people. One is John Clark, is the guru, is a postdoctoral student, is a PhD student John M. Martinez. So John Clark, he born in 1942 in Cambridge, UK. He did the PhD in 1968 from University of California, UK. Professor at the University of California, Berkeley at the time of awardee. So Michael H. Devarath in 1953, Paris, he studied PhD in 1982 from Paris Sud University, France. The professor at Yale University, New Haven City, University of California, Santa Barbara. John M. Martinez, born in 1958, he did the PhD in 1987 from the University of California, Berkeley, USA. Professor at the University of California, Santa Barbara, USA. Right now is doing that one. So means this work is around the 1982 to 1985. So they did this work. So that work is macroscopic quantum mechanical tunneling, and energy quantization in an electric circuit. How much money they will get? They will get the 11 million Swedish kroner, 11 million Swedish kroner, 11 million Swedish kroner, 11 million Swedish kroner is divided by 3. So 11 million Swedish kroner is divided by 3. 11 million Swedish kroner is divided by 3. So this much of money they will get it. In the Indian rupees, 1 Swedish kroner is equal to around 20 rupees is there. So 1 million is equal to 10 lakhs, 11 is divided by 3, around 37 or 36 lakhs rupees they are getting under the Indian currency. Clear? Now you have to see how this theory is coming. Science is not fixed subject. Science is changing from one day to another day, right? So in the first, in 1926, Erwin Schrödinger, he got the Nobel Prize in 1933. He invented the discovery wave functions penetrated into classically forbidden region. What he did discuss, there exists a finite probability of particles to pass the barrier, although it does not have the enough energy to do so classically. Means a lesser energy particle can penetrate through the higher energy barrier. What is the example? Alpha decay, radioactive decay, and fusion process occurs in the sun. So these are the example. A lesser energy particle can penetrate through the higher energy barrier. Classically it is forbidden, but quantum mechanically it is existing the first time in 1926, Erwin Schrödinger given. After some time, in 1960, Leo Esaki and Ivar Gaever awarded the Nobel Prize in 1973. This is the first half. One more scientist is there, Brian Josephson. That is the second half he got it. For their experimental discovery regarding the electron tunneling phenomena, he applied for the semiconductors and superconductors respectively. In 1960, Gaever experimentally confirmed that the existence of the energy gap in the superconductors, something predicted by John Bodin, Leon N. Cooper, and Robert Sheffer. In 1950, they invented the BCS theory. They got the Nobel Prize in 1972. So this theory is the BCS theory. They confirmed the experimentally superconducting phenomena. Who is John Bodin? In the physics, only physicist got the award, Nobel Prize twice in physics field. In 1956, he got the award for the invention of the transistor. In 1972, he got the award for the invention of the BCS theory of the superconductor. Clear? So first, the Erwin Schrödinger given the concept theoretically, a lesser energy particle can penetrate through higher energy barrier. Such type of process we call it as a tunneling process. Clear? So in 1972, so they got 1957 or 1960. So Leo Esaki and Ivar Gaever, they discussed this electron tunneling phenomena in semiconductors and superconductors. This is the quantum mechanical phenomena. We cannot see with our naked eye. Clear? In 1962, other half of the Nobel Prize, they got the award in 1973, Brian Josephson effect he got. So through this Josephson effect, superconducting quantum interference devices, that is the SQUID at the Bell Labs in USA. In 1962, Brian Josephson predicted that Cooper pairs can tunnel. Cooper pairs can tunnel without resistance across an insulating barrier, giving rise to a zero voltage current across a tunneling barrier between the two superconductors. He invented the Josephson effect, was experimentally confirmed at Bell Labs as early in 1963. In 1964, based on this Josephson effect, a sensitive magnetometer was discovered. That sensitive magnetometer is SQUID, that is the superconducting quantum interference device, was developed at Ford Research Labs. So, what is that Ford Research Lab? Also in US in 1963. Clear? So, this is the another effect. Now, you have to see in 1972, Sir David M. Lee, Douglas O. Oshroff and Robert C. Richardson awarded the Nobel Prize in 1996. How many Nobel Prizes are coming from this field once you have to see? They got the Nobel Prize for the discovery of the superfluidity in helium-3 nucleus, helium-3 molecules. Helium-3 can act as a fermion, but they can also form the Cooper pairs at low enough temperature, condense into the superfluid phase. So, they got the Nobel Prize. David M. Lee, Robert C. Richardson, Douglas D. Oshroff. So, these three people got the Nobel Prize in the presence of the superfluid phase. So, in 1978, Anthony Leggett is a great person awarded with the Nobel Prize in 2003 for pioneering contribution to the superconductors and superfluids. He suggested that the quantum mechanical tunneling between the two macroscopically distinct components of such a cat state could be realized in the superconducting circuits. So, till now all these people, so whoever the scientists are there, so what is those scientists? Erwin Schrödinger, the first scientist is Erwin Schrödinger. Erwin Schrödinger introduced about the theoretical concept, and so the Leo Esaki and Ivor Geyer, so that is the quantum mechanical concept we cannot be see, that is the microscopical phenomena, and Brian Joseph also microscopic phenomena invented the Josephson effect, and David Lee, Douglas D. Oshroff, Robert C. Richardson, they invented the superfluidity in the helium-3, that is also microscopic phenomena. But he got the Nobel Prize in 2003, that Anthony Leggett, he got the Nobel Prize in 2003. His research is superconductors and superfluids. He applied for macroscopic phenomena. Clear? So, this is very great invention. So, that invention in millikelvin temperature he did the, so this research along with PhD student Amir Calderia. So, Leggett investigated how the tunneling rates could be affected by weak remaining coupling to a dissipative environment. This is very important one he discovered. So, now you have to see, classically suppose one person is throwing the ball to that wall, what will happen? That ball should be bounced back. Classically is not forbidden, but quantum mechanically is that ball can pass through this wall. Such type of phenomena we call it as a quantum mechanical tunneling. Which one it is? Quantum mechanical tunneling. This phenomena we call it as a quantum mechanical tunneling phenomena. This phenomena we are going to call it as a quantum mechanical tunneling phenomena. How you see? So, classically it is not existing. If you have to take to the people, so people will claim you don't know anything like that, they will tell, but quantum mechanically it is existing. This is a great discovery. This discovery is the surprising discovery. So, whoever people uninitiative discovery. So, now you have to see, this is the macroscopic quantum mechanical tunneling, how it is one lever you have to take. So, in this experiment you are going to see this lever is in off state is there, this lever is in off state is there, automatically without applying anything. So, that lever is in on state, it is coming. How it is coming? The quantum mechanically suddenly voltage is appears. This is as if the lever moved from off to on state despite the barrier between the two. So, what happened in this experimental, we call it as a, this experiment we call it as a macroscopic. Which one it is? It is a macroscopic quantum mechanical tunneling. So macroscopic quantum mechanical tunneling. This is the diagram about the macroscopic quantum mechanical tunneling. Clear? So automatically this lever is off state to on state, it should be transformed. Clear? So that is very, very important. Once again you have to see, so this is the nucleus is there. Suppose you have to take the atomic structure, inside the nucleus is there. In the nucleus neutrons and protons are existing. So the surrounding there is a circular orbits are there. These neutrons and protons are bounded by this nucleus. So automatically this proton is coming out. So this proton is coming out. How it is coming out? So there is a binding system is there. Classically it won't come out, but even though these particles are coming out, such type of so phenomena we call it as a nucleus decay. That decay we call it as a alpha decay. Clear? So the nucleus is there, inside is a barrier is there. So this nucleus is coming out. Nucleus means entire nucleus, it won't come out. Some of the protons or neutrons is coming out. Such type of particles we call it as a, which one it is? That is the alpha particle is coming out. Clear? So that is very, very important. Once you have to see how it is coming out. Suppose if you have to take it as a parent nucleus XZA, you have to take it will become as a from protons 2 lost and mass number 4 losses, you are going to get it as a alpha particle. So this is the alpha decay is there. Clear? Suppose you are going to write it as a uranium 92 238, you are going to take so it will become as a thorium 9232. So 236 234 you are going to get. So thorium 92 234. So plus 1 alpha particle is going to coming out. Such type of process we call it as a alpha decay process. This is the another example. Now you have to observe the superconductors. So normal conductor, there is a electron, these electrons are the fossil, like this zigzag structure is there, they can move from one place to another place. But in a superconductor, they can form the Cooper pair, one electron is combined with another electron, one electron with combined with another electron. So there is a two conductors, two superconductors you have to keep, and so there is a junction is there. So this junction we call it as a Josephson junction. What you have to tell, this is the microscopic phenomena. From the macroscopic phenomena, these all Cooper pairs can form as a wave function, can form as a, which function it is, can form as a wave function. All Cooper pairs can form as a wave function, pass through this junction. This effect we call it as a Josephson effect. So this effect, these scientists used this effect and they did the research for the electronic circuits. Clear? Once again you have to see. So this is the superconductor 1, this one is a superconductor 2, there is a barrier is there, but even though some potential we got, some current we got, this is the Josephson effect or Josephson current is there. Instead of this, we are going to characterize it by the I naught is a characteristic temperature. You have to keep the RC circuit. This RC circuit can act as a high pass filter, can act as. So this filter, how much frequency is coming, that voltage we are measuring here. So this is the equivalent circuit of the Josephson junction. Clear? So based on this concept, the people are converted into the electrical circuits. So this is the great inventory. So now you have to see the potential when I is less than I naught. So what will happen? This is a minimum position is existing where I is greater than I naught. There is a deflection is there. What it is a V naught, V is greater than 0. A finite voltage is up here. When it is a minimum position, you are going to get it as a stable. So when it is the V naught, I naught is greater than I, it can act as a discrete system. So this discrete system, we call it as a energy quantization. So this one, 2, 3, this is, we call it as a energy quantization. Energy quantization, we call it as energy levels or discrete energy levels, you are going to get it. That's why macroscopic quantum mechanical tunneling and energy quantization in electric circuit, this is the theory they got the Nobel Prize. So what their theory, once you have to see, Berkeley group experiment, they discussed, he joined Michael Clark, he joined in 1969, he did the research based on the superconducting junctions and their applications he did. He invented the magnetometry and bolometry. What is the magnetometry? To find the magnetic field, we used the magnetometry. To find the radiation, we are using the bolometers. Radiation we are using, for measuring the radiation we are invented the bolometry. So his PhD student John Martinez, his postdoctoral student Michael Devereth, they did the research in quantum mechanical tunneling, macroscopic quantum mechanical tunneling, reasonable doubts, they did this one. So they set up the two experiments. One experiment is copper powder microwave filter, this is the first one. Another experiment is weakly coupled microwave controller. These two experimental setup they set up and they confirmed that macroscopic quantum mechanical tunneling phenomena experimentally and macroscopically in the electronic circuit, they discovered this one. So how they discovered, once you have to see in the classical regime, this is one happen. You have to see here normal temperature you are going to take here, your escape temperature you are going to take effective escape temperature you have to take the effective escape temperature, how it will come. So if the low temperature you are going to take it as a, so quantum junction is arises, how much current is making 9.498, here classical regime how much current is existing 1.383 only we are existing. This is the advanced one, we have to use this one. So now not only that, so based on this we are going to take it as a quantum tunneling effect, quantum tunneling effect. So this is the quantum macroscopic quantum mechanical tunneling. Based on this, energy is quantized. This is the first energy level. So this one is the second energy level. This one is the third energy level. You have to observe here. So 0 to 1, this line will come. 0 to 1 to 2, this line will come. 2 to 3, this line will come. So this is the discrete energy system. So this one is a, so energy quantization. Energy quantization, this one we are going to call it as a energy quantization is happening. So he invented this experiment. This is the experiment of the, which one it is? So this experiment is the John Clark invented the experiment to do the macroscopic quantum mechanical tunneling experiment. This is a powder connector is there, microwave contact is there, Cooper powder to filter the noise. So Cooper tubing is there. This one is the silicon chip with the Josephson junction is there. So all the beams of the Cooper pairs coming and passing through this Josephson junction. So in the chip level, this is the great invention of that. So these three people, John Clark and Michael Devereth and John Martinez, constructed an experiment using a superconducting electrical circuit. The chip that held this circuit was about a centimeter in size. Previously tunneling and energy quantization. Previously tunneling and energy quantization had been studied in the system that had just a few particles here. These phenomena appeared in a quantum mechanical system with billions of Cooper pairs that filled the entire superconductor on the chip. In this way, the experimental took quantum mechanical effects from a microscopic scale to macroscopic one he converted. This is very important thing he discussed. So this is experimental setup. So this is the quantization, energy quantization, how it will happen. This is the energy quantization from here to here, the level 1, level 2. This is the energy quantization while explaining the alpha decay. So now you have to change that. So electron spins, you have to write it in these Cooper pairs is coming and hitting. So there is a bulb is arising, that current is generated. This is the, which one it is, this effect we call it as a macroscopic quantum mechanical effect and energy quantization. Clear? So this is very important application diagram you have to see. What are the advantages in particle and theoretical benefits what we will get? So we will get the theoretical benefit. You use the quantum computer, so that is instead of zeros and 1 be able to use the qubit, that is quantum bits we are using. Clear? So who invented Nippon Electrical Company, the first time they invented the supercomputer based on this group. So based on this theory. Now another one is circuit quantum electrodynamics. Circuit quantum electrodynamics, also we invented this one by using the microwave resonator. So now instead of qubit, now people are using the transmon, is a sensitive to charge noise and used a number of efforts around the world. So to realize the large scale quantum computer, so around the globe we need to use. So not only that, in quantum optics we have to use, in superconducting circuits we are going to take it as a, so for a superconducting circuits we are going to use in quantum optics and quantum engineering we are using this one. The transistors in computer microchips are one example of the established quantum technology that surroundings us. So this year Nobel Prize Physics has provided the opportunities for developing the next generation quantum technology, including the quantum cryptography and quantum computers and quantum sensors. When this theory discovered around the 1982 to 1985, so around this time in University of California, under the guideship of John Clark, so they invented for 1982 to 1985, so maybe after 40 years, so they got the Nobel Prize, they honored, and nowadays we are enjoying the macroscopic quantum mechanical phenomena. Once again you have to see, in this theory 3 things are there. Quantum mechanical phenomena is already is there. So this quantum mechanical phenomena, they apply to the macroscopic electronic circuits. Quantum mechanical phenomena, tunneling, that is the tunneling phenomena. The second one is energy quantization. These 2 phenomena they are applying in a electronic circuit. You able to see the circuit will give enormous whatever the things man did not do, so those things that circuit can do. Such type of phenomena we call it as a macroscopic quantum mechanical phenomena in an energy quantization in an electronic circuit. For this discovery they got the Nobel Prize in 2025. So please share and subscribe and like our YouTube channel, like these theories, like the science and technology issues we will discuss in our YouTube channel. Listen and enjoy. Thank you so much.